other books that I have.
Yeah, now that you mention it, the name is ringing a bell. Clausius Clapeyron relation,
Yeah,
something like that. I couldn't tell you what it's about.
Oh, so that took away one of my possible. When I'm supposed to look and know which ones I can and can't answer. And if there was two I couldn't answer, well, then there's one I absolutely couldn't answer, and one that I just kind of had to brute force my way through, I guess.
Good morning.
Okay, how's it going, guys? Everybody see me and hear me okay?
Yes.
Yep.
I gotta crank up the volume here. Somebody say something. I want to make sure I got this turned up high enough.
We can hear you okay.
You can hear me okay. Okay. So I have 1 or 2 minutes past, so maybe we should go ahead and get started. I know this was an intense weekend for about half the class, so I hope you guys had a chance to recover on Sunday after a very grueling exam on Saturday. So I have a couple of logistical things that I should mention. Homework 1 was nominally due this past Friday, and so I took the submissions that I had. There were 7 that I had in hand as of Sunday morning, and I graded those. I'm not going to be a stickler about due dates and stuff for the homework, but I can't give solutions out until I have something in from everybody, or until I cut off submissions. So certainly for this week especially, I understand that people need a little extra time. So get me homework 1. If you've not turned it in yet, please get it to me as soon as possible. But we are moving ahead with the timeline. So homework number 2 was assigned on Friday, and I'll share screen in a moment and walk you through what's on that one. That is nominally due this Friday as well. So I'm going to try and keep on this regular weekly rotation, short homeworks, 2 problems each, about a week to do it. Hopefully that all works out pretty well. So let me share screen for a moment. and I will show you what is on homework number 2. You guys are seeing this okay, right?
Yes.
Okay, great. All right, so 2 problems on homework number 2. The first problem is very straightforward. This is sort of basic computations using spin. For your convenience, I remind you about the Pauli matrices and about their trace orthogonality property. And so most of these are simple comments that we made in class, that you can find the eigenvalues and eigenvectors for a spin pointing in arbitrary direction by taking the spin matrix made out of the Pauli matrices, S dot n for an arbitrary unit vector in spherical coordinates, and diagonalizing it. So you can diagonalize this and check it against the formulas that we derived in class. There is also a statement in class that spin 1/2 is special in that any spinner is an eigenvector of something. So I'm asking you to show that, take a general spinner for complex numbers alpha and beta, and show that they can be put into the form of these eigenvectors. So you can always find a unit vector n of which these are eigenvectors of the spin projection operator. And then this last one is sort of a simple application. If you have a spinner alpha beta, you can construct this 2x2 matrix, which is called the spin density matrix. And if you take this 2x2 matrix, you can decompose it. If you decompose it in terms of the unit matrix and the 3 Pauli matrices, then you can show that these quantities have a simple interpretation. The one is an unpolarized piece, it's a spin average. And this vector, this constant that multiplies the Pauli matrices, is the average polarization. So I ask you to show that you can take this 2x2 matrix and decompose it in this way, and that the constant which multiplies the Pauli matrices corresponds to that average value of the polarization. So none of these should be hard derivations. They should all go pretty quickly. This first problem is worth a standard 10 points. The second problem is about paramagnetic resonance. We talked about the precession of a spin or an angular momentum about a magnetic moment, about the magnetic field. And so this is a variation on that that's very important experimentally. The idea is, if in addition to having a strong magnetic field along the z-axis, you have a small perpendicular component, a small transverse field that is rotating at a certain frequency omega, then depending on what that frequency is, you can tune that rotation frequency of the field into phase if it's at the same frequency as the precession itself. That's a resonant state, so that you are rotating the field at exactly the same frequency that the magnetic moment is itself rotating. That is called paramagnetic resonance, and it's the basis of technology such as MRI, magnetic resonance imaging, where you are using that spin precession and the control that it gives you to manipulate spins in a system. So this is physically a very important problem. I would strongly recommend that you consult these pages in the textbook, which have a nice discussion of both classical and quantum paramagnetic resonance while you're doing the problem. So I try to walk you through the calculation. The first step is to calculate the magnetic field in a rotating frame. If you just take this magnetic field and you try and work with it, it's a real pain, because this is a time-dependent magnetic field. But that time dependence just comes from the rotation. So the problem gets a lot simpler if you change into a rotating frame of reference that rotates along with the magnetic field. In that rotating frame of reference, the magnetic field is time independent. And so you're supposed to show that this transverse field that rotates becomes constant. And effectively, that z component of the magnetic field changes, because in the rotating frame, the precession is slowed down. And you can interpret that as if the magnetic field were reduced. So this is the effective magnetic field in the rotating frame. And this is the one that you can really solve. So first, you argue sort of classically that this is what the magnetic field is that's going to drive the precession in the rotating frame. To see that quantum mechanically, you have to make a rotation transformation. So if you start with the Schrodinger equation with the full complicated rotating magnetic field, and you perform a rotation, a unitary rotation like we've discussed in class, then you should be able to show that the Schrodinger equation in the rotating frame, in terms of this psi r rotating vector, looks like this. And if you analyze these pieces, then I think you can convince yourself that this structure in brackets corresponds to this gamma dot b effective. That this is the combination of a rotation of the magnetic field and a reduction of its z component. And once you obtain this formula, this is an equation you actually have a chance at solving. This equation is really bad. So part B is about deriving that change of variables from the lab frame to the rotating frame, where the magnetic field is time independent. Once you have that, you can write down the solution immediately in the rotating frame and then transform back. And then what you should be able to show is solve for the spinner as a function of time. So if the initial condition is something that is magnetized spin up along the z-axis, then at later times you can find what the spinner is doing as a function of time. And if you compare this to the eigenspinors of the arbitrary unit vector, then you can tell exactly what direction the spin is pointing as a function of time. I should also mention, when I first uploaded this file, I had a typo where instead of 1, 0, I had 0, 1. I found it and replaced it very quickly, but if you had downloaded the PDF as soon as I first put it up, it had a typo in it. So please be aware of that. That could throw you off. So that's the exercise. This one is pretty long and complicated, so this is worth 15 points instead of 10. So take your time and work through this slowly. Again, I strongly recommend that you consult the discussion in the textbook as well to guide your thinking. But that's the content of the second homework. The problem 1 is a simple calculation exercise. Problem 2 is a more important physical application. Any questions about homework 2? Okay, great. If not, then let's dive on in with the new material for today. Any other business that we should discuss before we go for it? Okay, if not, then let's remember what we've discussed previously about angular momentum. So the key defining feature of angular momentum is its commutation relations. The commutator of angular momentum component I and angular momentum component J is I hr sum over k epsilon ijk lk. From this, you see that not all of the components of the angular momentum commute with each other, and so there are no eigenstates of L vector. The best you can do is simultaneous eigenstates of L squared and LZ. The eigenvalues of L squared are h bar squared L plus 1. And the eigenvalues of LZ are h bar times that eigenvalue LZ. Now, I should already make a comment here, which is generally we've been calling this quantum number M. At least for the purposes of today, when we're going to talk about lots of different kinds of angular momentum, I'm going to try to be really clear about which angular momentum component I'm talking about here. So I will refer to this as LZ today, because we're going to talk about LZ versus SZ versus JZ and the relation between all of these pieces. Okay, so this was the commutator algebra and the eigenvalues and eigenvectors that you can get. Crucially, we found that from this angular momentum algebra that all angular momentum is quantized, and they come in ladders, where the value of LZ differs by exactly 1 unit of H1. Algebraically, this was given through the behavior of the raising and lowering operators, L plus minus, which are Lx plus or minus I Ly. And we found that the action that these raising and lowering operators have on the state L, LZ gives you this specific eigenvalue, L plus 1 minus LZ plus minus 1, LZ plus minus 1. I'll copy this formula over again in a minute because we're going to use the hell out of this thing today. We are going to be taking ladders and raising and lowering them over and over again. And so the specific form of that square root that shows up is going to be a lot of the work that we're going to do today. If you're ever confused about the form for this L plus minus, remember that if you're at the ceiling of the ladder, you cannot raise it. And if you're at the floor, you cannot lower it. So if LZ equals plus L, then L plus should give me 0. So if I take this and I plug in LZ equals L and plus, then this term cancels that term and I get 0. You cannot raise the ceiling. Likewise, if LZ is equal to negative L and I'm on the floor, you cannot lower the floor. So if this is negative L and this is negative L and that's a minus, all of the minus signs conspire to again give you 0. So that's how you can double check that your signs are correct if ever you forget. Okay, the picture that goes along with this is that your angular momentum comes in ladders. So for instance, if I have an L equals 2 orbital angular momentum state, then there are exactly 5 allowed values of LZ. LZ can equal +2, +1, 0, -1, and -2. LZ equals +2, LZ equals +1, LZ equals 0, LZ equals -1, LZ equals -2. So you can think of it like a vector with fixed length whose angles are quantized, so that its z component always has to come in integer steps. So this is your picture of what the angular momentum vector is allowed to do in quantum mechanics. All right, all of this is true just because of the algebra of angular momentum. This is true whether I'm talking about orbital angular momentum, or whether I'm talking about spin, or whether I'm talking about a combination of the two. And that's the subject of today's lecture. All right, so what we saw previously is that if you have a particle or a system that has both spin and orbital angular momentum, the generator of rotations for a system that has both is the total angular momentum, is the sum of spin and orbital angular momentum. So we wrote something like this. We said, if my state psi is a vector, that psi rotates and my position rotates. This transformation is attained by a combination of a rotation of the position r, u of theta, and I'm going to call this orbital, as well as a matrix, u of theta spin, that rotates the original vector psi and the position r in space. So this is the operator that rotates the position r. This is always there, even if your particle is a scalar, so that there is no matrix. If there is a matrix with spin, then that gets rotated too. We said the orbital transformation is generated by orbital angular momentum, e to the minus I over h bar L dot theta. The spin part is a matrix which is generated in the same way, minus I over h bar spin dot theta. And since orbital angular momentum and spin act on totally different spaces, they are completely independent degrees of freedom, they commute with each other. This is a derivative that acts on the angles theta or the components of the vector r. This is a matrix that for any value of r scrambles up the components of psi. They are completely independent of each other, and so you generically have L commutes with S. Components of L don't commute with each other, components of S don't commute with each other, but L and S commute together. Okay, so in this way, we write psi prime of r prime equals e to the minus I over h bar j dot theta. Psi of r, where the generator of rotations is j equals L plus s. Okay, so now let's talk about the relationship between these quantities. So first off, the total angular momentum satisfies the algebra that it must. So it is nice to see that if I take the commutator ji and jj, this is in fact IH bar sum over k epsilon ijk jk. So if I take this definition and I plug in ji equals li plus si, plug this in here, Li with Lj has this commutation relation, Si with Sj has this commutation relation, and the cross terms Li with Sj are zero. Spin and angular momentum commute with each other. So first off, total angular momentum behaves like an angular momentum. That's good. We shouldn't take this for granted. That means that the eigenstates of J are again J squared and Jz. You can't have something that commutes with all of the components separately. The best that you can do is find simultaneous eigenstates of J squared, which is Jx squared, Jy squared, Jz squared, and Jz, which is Lz plus Sz. So let me write it down here. So in the same way, I can write down the eigenvalues and eigenvectors of J squared. J squared, Jz equals h bar squared j plus 1, jz. And the jz operator gives you h bar times the eigenvalue jz, jz. All right, so far it's exactly the same old story we've discussed 3 times now. So it's worth writing again that because the algebra is the same, total angular momentum also comes in ladders. So we found that orbital angular momentum L satisfies the angular momentum algebra. Orbital angular momentum comes in ladders with quantized Lz. Spin comes in ladders with quantized Lz. Because the total angular momentum is also the same, it has the same algebra, total angular momentum also comes in ladders that are generated by J plus and J minus. So the crucial piece of algebra that we're going to be working with today is the following. J plus minus is defined as Jx plus minus Ijy. Since Jx is Lx plus Sx, this is L plus minus plus S plus minus. Simple statement, but this is what contains the algebra that tells you how to relate the ladders to each other. The ladder of total angular momentum is controlled by raising and lowering of J. Separate ladders in orbital angular momentum and spin angular momentum are controlled by their respective raising and lowering operators. So the critical algebra that we're going to have, the formula that we're going to use 100 times today is this one. Just to repeat it, This is true no matter which kind of angular momentum I'm talking about.
Dr. Sears,
Yes.
just so I can figure, in that first parenthesis, should there be a plus and a minus? Or is it plus?
This one is always plus. So this one comes from the total angular momentum. This is always LL plus 1 or JJ plus 1, just like J squared. And then this one has plus or minus here.
Okay, this one thing.
Sure, no problem. Okay. All right, so the crux of all of this, the reason that addition of angular momentum is not trivial is because J squared does not simultaneously commute with LZ and SZ. So if I write out J equals L plus S operators, and J squared is J vector, if you like, J dot J. This is L plus S dot L plus S. If I expand this thing out, I get L squared like we had before, S squared like we had before, plus 2L dot S. Normally with operators, you have to worry about the order of the dot product, L dot S versus S dot L. But in this case, L and S commute with each other. They act on totally independent spaces. So you can just add the terms up in the usual fashion. And here's the problem. If I write this out in terms of components, L squared is good, S squared is good, LZ and SZ are good, but it also brings in all the other components. If you want, you can also rewrite this XY term in terms of L plus and L minus. That's sometimes useful. But the point that comes out of this is that J squared does not commute with LZ. And J squared does not commute with SZ. So J squared commutes with L squared. J squared commutes with S squared, but that Z projection does not play nicely with the addition of angular momentum in terms of total value of the angular momentum. So this statement here, which we've written algebraically, the non-commutation of these observables, is so important that it's worth writing out in words to try and get the physics across. So let me say this two different ways. States with definite values, LZ and SZ, do not have well-defined, total angular momentum J. And likewise, states that have well-defined total angular momentum J, that have well-defined rotation properties as a whole, do not have well-defined separate identities under LZ and SZ. equivalent to each other, and these are the words that I would associate with this non-commutation. You have two perfectly good pictures of the physics that are incompatible with each other. In one picture of the physics, I tell you separately what is LZ and separately what is SZ. Sometimes that's useful, but that picture is not compatible with total angular momentum and total overall rotation properties. If I fix LZ and SZ separately, I cannot answer for you uniquely what is the total angular momentum J. Yes?
You can't with the information given, or if you know LS and LZ, you just can't get the total.
The statement is that the states of definite LZ and SZ are a superposition of multiple different total angular momentum values J. And vice versa. A state that has well-defined total angular momentum J and JZ is a superposition of different ways to distribute that information between LZ and SZ. So you can have one or the other, but not both simultaneously. Either separate identities of spin and orbital, or total values, but not both. So mathematically, this is a statement that we are changing basis, that there are two equally good bases to describe the physics. One basis that tells me about LZ and SZ, in which J is some complicated operator. Or I've got the basis of J, total angular momentum, which has well-defined overall total angular momentum properties, but separate information about LZ and SZ, or L and S, are not well-defined, right? So these would be non-diagonal. So you can go to a basis in which this information is diagonal and that one is not, or a basis in which this one is diagonal and that one is not, but they do not commute with each other and you cannot have both. Is that clear? Okay. So this is the exercise of today. So this is a change of basis between one representation and the other. So this is probably a good point to mention that although it's very helpful to think of this as a physics problem, at the end of the day, it's not. At the end of the day, this is a purely math problem about the group theory of generators of rotations and one basis for that group theory and a different basis of that group theory. So you can find this problem in pure math textbooks where it's talking about the change of basis in group theory. But we, as physicists, have the extra intuition that comes from understanding how rotations and angular momentum. So we will leverage that intuition to understand how this math problem works. Okay. So a couple more comments before we dive into the nitty-gritty. This problem arises in multiple different contexts. So cases where you encounter this are cases where you need to know about the total rotational properties of a system. So you can talk, for instance, about total angular momentum of a hydrogen atom. So there you might be concerned with J equals L plus S, where your electron has some orbital angular momentum from its motion around the proton, as well as spin angular momentum together. And the overall properties of that atom, whether it rotates like a vector or rotates like a scalar, depends on what quantum states you're in. Similarly, you can talk about the total spin of a composite particle. We're not talking yet about identical particles, but if I have two electrons, then I can put spin 1/2 and another spin 1/2 together and add up their angular momentum and build a composite object out of it. So I can have J equals S1 plus S2, two different spins, and add those together. So this is a problem that arises in nature. You'll have a particle like the deuteron, one proton and one neutron bound together to make a single object. That object has total angular momentum. It could be a scalar, could be a vector. Depends on how you add together those two angular momentum. And how you describe the composite particle is based on how you add up the spin of its constituents. This also arises in a different context, which is very important, which is spin orbit and spin-spin coupling. coupling of angular momentum. So if you have a Hamiltonian that contains spin-orbit coupling, this is one of the most important corrections from the fine structure of the hydrogen atom. You can have a Hamiltonian that includes something like some constant G L dot S. Physically, this arises because one angular momentum produces a magnetic field. The second angular momentum wants to align with the magnetic field created by the first one. So what you have is an effective relationship that tries to line up two different kinds of angular momentum. That L dot S term arises as part of the cross terms when you expand out J squared. So you can simplify this if you write this as G over 2, and then this is J squared minus L squared minus S squared. So I expand out J equals L plus S. I cancel out the perfect squares. I'm left with only the cross term, L dot S. So the problem of how do I diagonalize a Hamiltonian like this is the same problem. You diagonalize it by finding the eigenvalues of J. The eigenstates of total J are the eigenstates of this Hamiltonian. This also arises similarly for spin-spin coupling. You have a Hamiltonian that looks like G S1 dot S2. And again, in the same way, you can expand it out. This is a part of the hyperfine structure of the hydrogen atom, where you have a coupling between the spin of the electron and the spin of the proton. So my point here is that there's lots of different physics cases when you encounter this problem. But for the purposes of our discussion today, none of these contexts matters. The solution is the same because the algebra of angular momentum is the same, no matter which kind you're talking about. Can be spin, can be orbital, can be a mixture of the two. The problem of addition of angular momentum is perfectly general. Okay, so this is what we're doing and this is why we care. We are going to want to include physics like this, and we are going to need to understand composite systems of this type. How many minutes time? It's like 48 minutes. Okay, maybe one other term that I should give you before we dive in all the way. The term that you should associate this, if you want to Google something, are Clebsch-Gordan coefficients. So ultimately what we are performing here is a change of basis. That change of basis is equivalent to a rotation matrix. That matrix is called the Clebsch-Gordan coefficient matrix. So specifically what we are doing is we are taking the basis we want that has well-defined total angular momentum values J and Jz, and we are expanding this to find that representation in the basis of Lz and Sz. So if I sum over all allowed values of Lz, and I sum over all allowed values of Sz, then I can write this as L, Lz, S, Sz, so all I've done is I've inserted a complete set of states. That complete set of states is the complete set of separate angular momentum and spin information. So this basis is sometimes called the product basis. It looks like L times S. So here I have separate information about Lz and Sz, and I have a change of basis matrix. This matrix of coefficients are the Clebsch-Gordan coefficients. For lack of a better term, we can talk about this one as being the total basis, total angular momentum basis, or maybe the sum basis. So if you look around on the internet, if you want to know more, Google Clebsch-Gordan coefficients. There's tons of references out there that can describe these. There are nice tables maybe we will show one of those tables next time. Today, we're going to concern ourselves with how to calculate what goes in those tables. Okay. So without further ado, let's consider a specific example. And I think this quote-unquote simple example is going to take the rest of class to work out. So let me take L equals 1, S equals 1/2. For now, I'm concerning myself with spin plus orbital angular momentum in the context that we've derived this in. And there is an even simpler example than this if I have spin 1/2 plus another spin 1/2. We'll probably do that one next time. All right, so what are my allowed values here? If L equals 1, then what are my allowed values of LZ? 1, 0, minus 1. If my spin is spin 1/2, what are my allowed values of SZ? Plus 1/2 and minus 1. I've got 3 possible choices for LZ, 2 possible choices for SZ. How many total states do I have? How many linearly independent states are there? 6. I have states with LZ equals any of these times SZ is any of those. So in total, there are 6 independent states. So that means that when I write down the set of all states, I'm just going to write LZ, SZ. Since I know L equals 1 and S equals 1/2 for the entirety of this discussion, the notation is messy enough already. I'm just going to call these states LZ, SZ. These states form a 6-dimensional vector space. So, specifically, if I want to write this out, the matrix of such states, or the vector of those states, is plus 1, plus 1/2, plus 1, minus 1/2, 0, plus 1/2, 0, minus 1/2, minus 1, plus 1/2, minus 1, minus 1. So these are the states where right now I'm labeling this first number is LZ and that second number is SZ. Now let's start thinking about the total values of angular momentum that come with this. J itself is complicated, but JZ is simple. JZ is LZ plus SZ. The problem comes when I ask for that total angular momentum quantum number J, but JZ I can immediately read off this list. If this is my value of LZ plus 1, if SZ is plus 1/2, then JZ is equal to 1 plus 1/2, this is plus 3/2. Likewise, I've got plus 1 minus 1/2, this is plus 1/2. 0 and plus 1/2 is also plus 1/2. 0 and minus 1/2 is minus 1/2, minus 1 and plus 1/2 is also minus 1/2. Minus 1 and minus 1/2 is minus 3/2. So when I start thinking about my total values of angular momentum, JZ is the place to start. 2 things to point out. First off, that uppermost value and the lowermost value are completely unique. This state, which has minus 1, minus 1/2, is the only state that has JZ equals minus 3/2. This one, which has plus 1 and plus 1/2, is the only one that has plus 3/2. On the other hand, these 2 states and these 2 states are degenerate. There's going to be some mixing going on in here. So knowing what we know about the algebra of orbital angular momentum, that angular momentum always comes in ladders. I see that I have a maximum value of JZ of 3/2, a minimum value of JZ of minus 3/2. There is no other choice other than for this to belong to a ladder of states. that has plus 3/2 at the top, minus 3/2 in the bottom, and differs by 1 unit of angular momentum each time. So let me try to draw a picture associated with this before we actually do the calculation of those coefficients. So we start off with L equals 1. There are 3 allowed states for L equals 1. I have LZ equals plus 1, LZ equals 0, LZ equals minus 1. So this is my orbital angular momentum vector with magnitude 1. It's allowed to point either all the way up in the xy plane or all the way down. And so these are the 3 values. My spin has value plus minus 1/2, and it's either pointing up or it's pointing down. So in addition to this, I can have 2 possible states. I can have SZ is plus 1/2, SZ is minus 1/2, and so on. So when I ask myself, what are the total values of JZ that I can get? I have this one, and I have this one. So this corresponds to a total value JZ equals 3/2. If I add spin 1 up, or orbital angular momentum plus 1, spin plus 1/2, that gives me plus 3/2. Likewise, at the bottom, when they're completely aligned and pointing down, I have JZ equals negative 3/2. This must belong to a ladder. If this is all the way up, then this tells me the magnitude of the vector. And these comes in steps of 1 unit of angular momentum. So the next value that I can have is this one. This is JZ equals plus 1/2. The next one that I can have is this one. JZ equals minus 1/2. So I immediately know, because I know the algebra of angular momentum, that these extremal states, all the way at the top and all the way at the bottom, must be the endpoints of a ladder. And somewhere in between, I'll have to have JZ equals plus 1/2, JZ equals minus 1/2. And I see how I can build that state either by having orbital angular momentum plus 1, spin minus 1, or minus 1/2, or orbital angular momentum 0, spin plus 1/2. Either one gives me that same component JZ. Okay, so what we're going to find is that when we make this transformation, there exists a ladder. How many states are in this ladder? 4. I started off with a 6-dimensional vector space. This ladder encompasses 4 dimensions worth of vector space. How many dimensions are left over? 2. So this ladder by itself is a self-contained 4-dimensional vector space. Angular momentum always comes in ladders. If that 4-dimensional ladder didn't use it up, what must be true? There's got to be another ladder that has those extra 2 states. Those 2 states have to be made up of this degeneracy, right? So we said this state is unique. Somewhere in here, I pick out one of these states to be the plus 1/2 part of that ladder. I pick out some part of this one to be the minus 1/2 part of the ladder. This one is unique again. That's the bottom of the ladder. So whatever combination I pick out of here to belong to ladder number 1, there's another combination, an orthogonal combination, that is independent of the first one and uses up that degeneracy. So the fact that I've got twice as many states here tells me that I've got another ladder with those same values of JZ. So I'm going to have JZ equals plus 1/2, JZ equals minus 1/2. This ladder is 2-dimensional, and this will exhaust the 6-dimensional vector space we started off with. So what we're going to find is that the allowed values are J equals 3/2 for the total angular momentum, and that contains 1 ladder. And we know how to generate the entire ladder. The other one is J equals 1/2. That's its own separate ladder. We cannot find this ladder from that ladder. We find this entire ladder, and then we look at what's left over. and then we assign what's left over to its own ladder, and we figure out its states. That's the procedure. Is the physics of this clear? Because it's very easy to get lost in the action. All right, so the starting point is the extreme end of the ladder, the one that we know is unique. You can decide whether you want to start at the very top or the very bottom. For the purposes of today's discussion, I'll start at the very top, and we'll generate this ladder by lowering it. So the starting point, step one, is to recognize that the top state of the maximal ladder is unique. So I would say JZ max equals LZ max plus SZ max. And this is just L plus S. The maximum value of LZ is L, the maximum value of SZ is S. And if this is the maximum value of J, then this must be JZ equals J, the maximum value of the J ladder. So what this is telling me is that I can uniquely identify the state J equals L plus S, JZ equals J. So this is the ladder who has maximum magnitude, full magnitude of L plus full magnitude of S, and JZ is completely aligned all the way up. This state can only be LZ equals L, SZ equals S, plus L plus S, plus J. Now, in principle, I could have a phase factor here. You could, if you really, really wanted to, choose to write e to the I phi for some complex angle phi there. We're not going to do that. There's no point. It makes the algebra more complicated. It is conventional to choose this factor to be 1. So up to an arbitrary complex phase, we start off by observing that the top state of the ladder is unique. Once we have the top state of the ladder, we know how to use the algebra of angular momentum to generate the rest of the ladder. We're going to use the lowering operator J minus, acted on that state, and that will give us all the other states in the ladder. All right, so this is where we're going to use the hell out of that formula. All right, so if I start off with the state, in this case, J equals 3/2 is the maximum value, and JZ equals plus 3/2. And I act on it with J minus. I know from the algebra what J minus is going to do to JZ. On the other side, I write J minus equals L minus plus S minus. And I write this in terms of the product basis. This is LZ equals plus 1, SZ equals plus 1/2. Let me write the formula that I'm going to need a bunch of times. All right, so in general, I'm gonna have J minus acting on the state J, Jz is H bar square root J plus 1 minus Jz plus minus 1. And then that returns back to state J with Jz subtracted by 1. This is true no matter which kind of angular momentum I'm talking about. So if I'm talking about the total angular momentum J, here I'm going to plug in J equals 3/2. So on the left-hand side here, I'm going to get H bar square root. I have 3/2 times 3/2 plus 1 is 5/2 minus Jz is 3/2 times 3/2 minus 1, 1/2. And this is going to lower that state. J equals 3/2, Jz equals plus 1/2. This is now the second state in the ladder. On the right-hand side, I'm going to do the same thing twice. One step which lowers LZ and gives me one number. A different step that lowers SZ, going to give me a different quantum state and a different coefficient. So if L minus acts on LZ, I'm going to get H bar square root of L is 1 times L plus 1 is 2 minus LZ equals 1 times LZ minus 1, that's equal to 0. And after I lower LZ, this is going to give me the quantum state LZ equals 0, spin SZ still equals plus 1/2. This is the first term where I took L minus and I acted only on this piece of information. So LZ went down, SZ stays the same. The second step is I now lower the spin as well. H bar square root, spin is 1/2, so I have 1/2 times 1/2 plus 1 is 3/2 minus SZ is plus 1/2, SZ minus 1 is negative 1/2. This is going to give me a state that left LZ alone. LZ equals plus 1, but lowered the spin. SZ equals minus 1/2. You can see why this starts to get messy. All right, so what do I have on the left-hand side? I have H bar. This is 15 over 4 minus 3 over 4. 15 minus 3 is 12. 12 over 4 is 3. So this is H bar square root of 3 on the left-hand side. Equals, I'm going to put this in a box. All right, on the right-hand side, this is just square root of 2 times the state LZ equals 0, SZ equals 1/2, plus 1/2. Plus the other combination. This is 3/4 minus a negative is plus another 1/4, so that's just 1. Plus H bar, this is the state LZ equals minus 1, plus 1, SZ equals minus 1/2. So now I can cancel units, and I can divide through, and I get something sensible. J equals 3/2, Jz equals plus 1/2, equals root 2 over 3. LZ equals 0, SZ equals plus 1/2, plus 1 over root 3. The state LZ equals plus 1, SZ equals plus 1/2. Minus 1. All right, we have now found the second state in the ladder. The second state in the ladder has Jz equals plus 1/2. It is a linear superposition of the states where that plus 1/2 total came from 0 plus 1/2, as well as plus 1 minus 1/2. It is a combination of the two. That combination is uniquely dictated by lowering the uppermost state. A nice cross-check to make sure that you didn't lose a factor somewhere in the arithmetic, which is very easy to do. This state is correctly normalized. I have square root of 2/3, that's 2/3 probability of this measurement. Square root of 1/3, 1/3 probability of this measurement. It all adds up to 1, so I didn't screw up the factors. Notice that this is only one possible linear combination of these two states. You can always find a combination of these two that is orthogonal to this. That's going to be the other JZ equals 1/2 state belonging to the second ladder. We're going to use that requirement to start the second ladder when we're done with the first one. All right, this step is just one that we repeat over and over again. Checking time, I see I have 15 minutes here. Let's bite the bullet and do one more step like this, just for the practice. All right, now I have this state, I can lower it again. J minus acting on the state, J equals 3/2, JZ equals plus 1/2, equals L minus plus S minus acting on all of that crap. Root 2/3, L minus plus S minus acting on the state, LZ equals 0, SZ equals plus 1/2. Plus 1 over root 3, L minus plus S minus, acting on the state LZ equals plus 1, SZ equals minus 1/2. So now you see how bad it's going to get. These terms are going to proliferate. Every time you lower it again, for every term you generated on the right-hand side, you have the possibility of splitting it up even further. But fear not, hope is not lost yet. One of these terms is 0. Who can tell me which one?
The second one, when you can't lower SZ.
When you cannot lower SZ further. SZ is already at minus 1/2 at the bottom of its ladder. S minus acting on SZ equals minus 1/2 is 0. Very good. I can lower LZ again. If spin is up, I can lower the spin. This one, I can only lower LZ. All right, so let's bite the bullet and see what we get. On the left-hand side, I have square root of H bar square root. Again, same as before, 3/2 times 5/2. That's 15 over 4. Minus, now I have JZ is plus 1/2. So that's 1/2 times 1/2 minus 1 is negative 1/2. This is going to give me the state J is 3/2, JZ is negative 1/2. All right, on the right-hand side, first term, I have square root 2/3. From L minus, I'm going to get H bar square root. L times L plus 1, that's 1 times 2, minus LZ is equal to 0, so the second term is 0, minus 0. That algebra is not so bad. And when I lower LZ, I get LZ equals minus 1, SZ equals plus 1/2. That's what I get by lowering LZ on the first term. I also have to consider lowering SZ on the first term. Plus root 2 over 3, H bar, square root. I have 1/2 times 3/2, that's 3 over 4, minus SZ is plus 1/2, SZ minus 1 is negative 1/2. This is going to give me the state LZ equals 0, SZ equals minus 1/2. All right, I'm done with the first term. From the second term, I only get one piece, just from lowering LZ. 1 over root 3, H bar, L minus, acting on this state, is going to give me L times L plus 1 is 2, minus LZ is 1, LZ minus 1 is 0. And this is going to give me the state LZ equals 0, SZ equals minus 1/2. So here's the second part of fear not. Even though we proliferated and generated 3 terms, 2 of these get the same quantum state back by different avenues. This state is the same as this state. So their coefficients just add up. it doesn't matter what order I lowered it in. This one I lowered angular momentum and then I lowered spin. This one I lowered spin and then angular momentum. Either way, it takes me to the same point. All right, so let's clean it up. I have 15 over 4 plus 1/4. That's 16 over 4. 16 over 4 is 4. Square root of 4 is 2. So on the left-hand side, I have 2 h bar. J is 3/2. Jz equals minus 1/2 equals. All right, this is the only contribution to this term. I have square root of 2/3 times square root of 2. So this is h bar 2 over square root 3. LZ equals 0. Sorry, LZ equals minus 1. SZ equals plus 1/2. Plus, in the second term, I have a combination of things. I have h bar, so this was 3 over 4 minus is a plus 1/4, so this is 1 inside of the square root. So this is root 2 over 3 with the h bar from the first term, and this is another root 2 over 3 h bar from the second term. LZ equals 0, SZ equals minus 1/2. All right, so now I clean things up. I'll cancel the 2h bar. 2h bar goes away, and I've got 2 of these things. So this is 2 root 2 over 3, and I cancel the 2h bar. And so I end up with something that looks familiar. I have 1 over root 3, LZ equals minus 1, SZ equals plus 1/2, plus root 2 over 3, LZ equals 0, SZ equals minus 1/2. Again, correctly normalized. That's a good indicator you probably didn't mess up the arithmetic somewhere. It's no accident that these coefficients are the same as the ones that we had before. Before, when we had the state Jz equals plus 1/2, built out of anti-aligned spin and angular momentum, and LZ equals 0, spin equals plus 1/2. Now those are all reversed. These are related by a discrete symmetry called parity symmetry. If you take the z direction and you flip it, if I flip it in all of these components, then I relate the two matrix elements to each other. In this case, they are related with equal sign. For the opposite ladder, we'll find that they are related by an opposite sign. So suffice to say that when you are doing the long calculation, you do not have to calculate the entire ladder. It's enough to calculate the top half of it. Once I've calculated Jz equals plus 1/2, I can immediately deduce the same coefficients or same coefficients with a minus sign from Jz equals minus 1. All right, suffice to say that if you repeat the lowering operator one more time, you find again that the bottom state of the ladder is unique. J is 3/2, Jz equals minus 3/2 is uniquely equal to the state LZ equals minus 1, SZ is minus 1/2. This coefficient is again automatically 1. If we defined the upper state of the ladder to be coefficient 1, then in this case that gives us the lower state of the ladder has coefficient 1 also. These are again related by parity symmetry. The lower half of the ladder is related to the upper half of the ladder. Okay, I have just a few minutes. I think you get the idea about applying the raising and lowering operators. The strategy is to start with the extreme state of the ladder, which is unique, and then use the algebra to fill in the rest of the ladder. Once you're done with one ladder, you've got to find the next one. The algebra of one ladder will never give you the other one. So what we've found now are the J equals 3/2 ladder. the states of the J equals 3 halves ladder. JZ equals plus 3 halves, JZ equals plus 1 half, minus 1 half, minus 3 halves. So to summarize, we found the states J, JZ, given in terms of the states LZ, SZ. So we found 3 halves plus 3 halves is uniquely equal to plus 1 half. And the state 3 halves plus 1 half is the superposition 1 over root 3 plus 1 minus a half plus root 2 over 3, 0 plus a half. And then the lower states of the ladder, 3 halves minus a half was 1 over root 3 minus 1 plus a half, root 2 over 3, 0 minus a half, and 3 halves minus 3 halves is uniquely equal to minus 1 half. So this is the result of the algebra that we just did. Maybe now you can see my point more clearly about the symmetry of the coefficients between the upper half of the ladder and the lower half of the ladder. To find the second ladder, I have to find the independent combination, which is orthogonal to the one that showed up in the first ladder. So I'm going to take this state, and to find the state in the second ladder, J equals 1 half, JZ equals plus 1 half. This is some unknown linear combination of alpha plus 1 minus 1 half plus beta 0 plus a half. And my requirement is that this state be orthogonal to that one. I also have to require that it be normalized. Everything else I can pick by convention. So it is possible, and we will do it, to conventionally choose both alpha and beta to be real. And if they're real, the normalization condition is alpha squared plus beta squared equals 1. No absolute values. It's also arbitrary which one you choose to have the plus sign in it. We will conventionally choose alpha to be the positive one. Alpha greater than 0. Just meaning that whenever you call the first angular momentum, the convention is to pick the first one to be positive, when the first one is not. Okay, so my orthogonality condition tells me 1 over root 3 alpha plus root 2 over 3 beta is equal to 0, and I have alpha squared plus beta squared equals 0. And together, this uniquely gives me alpha is square root 2/3, beta is negative 1 over root 3. I am out of time. 3 minutes. Good. All right, so with this gives me J equals 1 half, JZ equals plus 1 half equals positive root 2 over 3. LZ equals plus 1, SZ equals minus 1 half, minus 1 over root 3. LZ equals 0, SZ equals plus 1 half. From here, you're at the start of the game all over again, level 2. Now take this one and start applying the lowering operator over and over again until you generate the entire ladder. In this case, there's only two states in the ladder. So if you just apply J minus, you'll get it immediately. It's also related by parity symmetry. Let me jump straight and give you the answer. Minus 1/2 is minus root 2 over 3. LZ equals minus 1, SZ equals plus 1/2, plus 1 over root 3, LZ equals 0, SZ equals minus 1/2. So these are the states in that second ladder. Okay. So this is the complete solution to the problem. We started off with a 6-dimensional vector space that came from a product of 3 possible values of LZ times 2 possible values of spin 1/2 SZ. And we decomposed it into a set of a ladder of 4 states, a 4-dimensional vector space with J equals 3/2, and a separate 2-dimensional vector space with J equals 1/2. So in that infuriating way mathematicians have of writing something incredibly complicated down in a beautifully simple way, this arithmetic problem is written as 1 times 1/2. This is L equals 1, tensor product S equals 1/2, can be decomposed into 3/2. This is the J equals 3/2 ladder plus direct sum 1/2. J equals 1/2. So if you read mathematical sources on this, they will write the expression in this way, which 1 times 1/2 equals 3/2 plus 1/2 is an unbelievably compact way of expressing the very long amount of arithmetic that we just did. But it contains all of this information, a product of a spin 1 state and a spin 1/2 state, decomposes into a